All right, everybody. Welcome back to the class. So we're gonna start with the paper presentations, and this week's paper presentations is on wireless security. If you remember last week, we talked about uh, various different problems in wireless security. There are like traditional and conventional problems that it's always important and one has to pay attention to, and it's an active area of research, including network security, different protocols for crypto and so on. We try to kind of cover a little bit of more of like unconventional, non-traditional ways of we need to think about wireless security. We talked about privacy aspects, and the first paper is actually about that essentially what it does is looking at this fact that many of the activities in your wireless Wi-Fi, for example, or as the paper going to show you, but by various different ways of communication, including Bluetooth and Wi-Fi, can actually be tracked. So they're not really breaking any crypto algorithm here, or not really accessing your data, but just tracking the behavior of your system in order to gain some insight. And as your classmate is going to describe, this can actually reveal some interesting information about the system. For example, the patterns of the user when they're home, how many people are home, things like that. So pretty important stuff in terms of what can be actually extracted. Then we're going to also talk about various different other aspects of wireless security. They're going to be a fingerprinting paper and so on that I'm going to describe once the student's going to present it. Okay. So without further ado, let's just start with this one. Yes, whenever you're ready. Yeah, you don't need to sit, you can stand. It just picks it up.
Okay. So my name is John. Me and my group, Arjun and Anouk, are going to present Peekaboo. I see your smart home activities even encrypted. So what's the problem here? The problem is the vulnerability of IoT devices to privacy attacks. These devices, such as smart bulbs, smart switches, and smart speakers, they were designed to improve living standards through automation and convenience. However, it also automatically exposes users to risks due to the sensitive information they collect and transmit. So why is it dangerous to have your private information getting collected and transmitted? Here are some examples, such as the attacker can infer when the home is empty by analyzing smart light bulbs patterns, posing a burglary risk. Also deduce personal habits and lifestyles by monitoring smart appliance usage, leading to privacy invasions. Also, eavesdrop on conversations or gather data about health conditions through smart speakers and health monitoring devices, compromising personal and sensitive information. These examples highlight the privacy risks associated with unsecure transmission and processing of data from IoT devices in smart homes. So the background of the problem is that the attack utilizes machine learning techniques to passively sniff network traffic from smart home devices and sensors, effectively identifying devices, types, states, and ongoing user activities, even when the communications are encrypted. So how is this possible? It is possible to infer smart home activities even when the data is encrypted, because the attack leverages unique traffic patterns generated by IoT devices during their operation. These patterns, such as the size, timing, and the frequency of encrypted packets, can automatically reveal information about the device type and the actions being performed. By analyzing these patterns with machine learning algorithms, attackers can deduce the presence and the activities of smart home devices without needing to decrypt the traffic. This method exploits the fact that encryption secures the content of communications, but not necessarily the metadata or patterns of traffic, which can still be revealed.
So I'm just going to give you a brief overview of the multi-stage privacy attack, right from sniffing Wi-Fi networks or Bluetooth or Zigbee networks to kind of inferring how a user behaves within the home. So I'm going to just walk you through all the steps that the researchers took to kind of get there. Um, Yeah, so the first three steps are device identification, classifying a device state, and also detecting the device state. For the device identification, they used fairly simple methods, actually. They would get metrics such as the packet length or the mean arrival time, and they would organize that data, pass it through K-means classifier, supervised learning models, and yeah, through that, they would be able to successfully identify what kind of a device is it? Is it a modem? Is it like a smart bulb? Is it a sensor? Yeah. For Zigbee, in fact, something interesting is that they got 93% accuracy with their devices, probably because that's slightly more simpler network. And to identify the device state, they receive a stream of bits. They use slightly different metrics such as inter arrival time, and now they have to concretely classify that into okay, what is the device really doing? Is it like on, off, maybe for the bulb? Is it surfing on Amazon for a modem? And they also use a K-means classifier for that, and also random forest uh, classifiers as well. Yeah, and just moving on to probably the last stage of the attack, but probably the most important is they want to extract varied device features from this data. So they would separate all the data that I spoke about, all the classifications into, say, timing features or device features, say for smart bulbs or sensor features. And then they would organize that data, again, use machine learning to, and then they created like classes for user activities, say a user controlling a device that would switch on a smart bulb or a user moving from one place to another. And that organizing in these features and creating these classes helps them build a model like what I've shown here. So here the user is outside and then he walks into the hallway. So if you have data about the sensor and the light bulb, then you can obviously correctly model that. Yeah. And yeah, they achieve like a 94% accuracy on all of their tests for inferring user activity. Um, A proposed solution against this is probably spoofing network traffic. So you're injecting false data. So for device state detection, accuracy decreased by about 57% for the researchers, and for classification, it reduced to 15% accuracy. If I would connect this to something that we've learned in class, I would say that this is kind of like sensor transduction, but in reverse, probably like um, yeah.
I'm gonna quickly go over some of the methods they use again and like the evaluation methods. So how they were able to tell which strategies were most effective. So again, back to the device identification stage, we have basically a bunch of commonly found devices, and they would find like metrics like their mean package length, inter-arrival time, standard deviation, and then map those onto different like consumer devices. And then that's how, and then after using a classification algorithm, they were able to mostly with pretty good accuracy figure out which device corresponded to that data. And so here we have the like F1 scores plotted along with the accuracy metric, and you can see that they did a pretty good job for just the identification part there. And then when identifying the device state, they would have like an extra trees classifier to bring the number of features down from 795 to 197. So for that, they would use like this program called TS Fresh, which is like a time series analysis tool that calculates certain metrics using that time series data. and then extracts the features out of it. And then after we have those features, it's just simple, like, just test different ML classifiers on it, see which one performs the best. And so they did a standard 5-fold cross-validation, and turned out that random forest got the highest score with that, with the 92% F1 score. And then after we had that classification, we could move on to inferring information about user activities. So and for that, they used a hidden Markov model, which is something like displayed on the bottom there. And then, so for this final step, they had 6 different types of activities. They mainly differentiated between activities that were time independent and time dependent. So time independent ones would just be like where a user is, like where they're located, or if a particular device they're interacting with, or it's left on or something. And then activities 4 through 6 were more like moving around, like going in and out of doors, stuff like that. Often they might even involve like multiple different devices and information like, interacting between all of those different devices. And so for the first set, the time independent ones, they were pretty much able to get the state pretty much every single time. And then accuracy diminished a little bit when working with the time dependent tasks to about 95%. And then, so for the future work, a lot of these smart devices are very diverse in time. So they're the protocols they use, the hardware they use. And but in this paper, we still had like a generalized attack, but this diversity does kind of help guard against these types of attacks in general. And so even being able to like keep this diversity and can maybe conceal it, or even add like artificial diversity in this case could help prevent, you know, these types of generalized attacks in the future. And then the paper also offered another more complex strategy, which would involve trying to hide the source and destination of the packets and where they came from. And one thing that we found to be particularly interesting was that this whole strategy could be extended for a remote attack. So someone who's not even like nearby through a malicious ISP could access like IPs and identify these different devices and the activity corresponding to it. So that kind of raised the question, like, which data might be more sensitive? Is it like the local data that's communicating with nearby devices in your home, or is it the information you're communicating with like big servers? And then lastly, since this is a multi-stage attack, if you do mess up on an earlier stage, that will influence the results you get in the later stages, and so that adds to the complexity a little bit. For example, like if you don't identify the device correctly, then you don't exactly know which information corresponds to like which activity for that particular device. And so yeah, that's about it. So
All right, thank you so much. Anybody has any questions? Yeah, as I said, this is an example of how just by looking at the traffic, one can extract interesting information. And I think your point is actually very interesting and valid as well, that you don't need to necessarily be physically, you know, close to the device. I mean, I think the attack that these guys were considered was like a device that is within the same vicinity, but essentially as long as you can kind of observe this network packets anywhere else in the world, you can technically do the same attacks, which is an interesting thing. Although some of these require that you actually access physical packets, which is a slightly different. So like you can attack this at many different, you know, layers of network, but definitely you can attack it from far away as well. All right, thank you guys. Appreciate it.
thank you.
All right, next group. So the second paper is about relay attacks. We actually talked about relays and distance bounding. And I told you that your student's gonna your friend's gonna present the actual attack. So this is actually one of the first attacks that shows that in fact you can relay information between a transmitter and receiver without really replicating the transmitter. We probably have seen videos. I don't know if these guys are gonna show you some videos, but there are lots of videos in the internet showing that, for example, guys like, stealers with like antennas goes next to next to a garage and actually kind of like attack a system. If you haven't seen it, I definitely recommend you to kind of like, just look at YouTube and search relay attacks and you will see lots of examples of that. But let's actually see how it works, and then I'm gonna talk more about it. Let's see if I have the coordinate. Yes, good. So whoever is speaking, just come this way, okay? All right, please.
Hi, this is our presentation on relay attacks on passive keyless entry and start systems in modern cars. I'm John.
Chris, what's that?
So just some quick background. So basically, passive keyless entry and start, which is just acronymed as PKES. These systems basically just allow car owners to just unlock and start their vehicles just without physically handling their keys, which is pretty much shown in most models of new cars. And basically, it just detects the key's presence when it's really close to the car. So basically, it just enables you to start it, the ignition, without actually physically having to turn and unlock a door or use an ignition key. So basically, just mainly for convenience purposes in modern cars. So just a quick introduction. Basically, this paper talks about how to use relay attacks on PKES systems. And basically, they just built like these efficient but inexpensive wired and wireless relays. So basically, just relaying messages between the car and the smart key. So independent of the system modulation and then other security measures, and which allows them to like kind of bypass that. And so they evaluated this on 10 different car models for between 8 manufacturers, and they all demonstrated vulnerability to these relay attacks.
Right. Before we talk about attack, I'll give a slightly more detailed overview of the PKES system. So we have two parties communicating with each other, one being the car, the other being the key. The car would periodically probe the air channel to see if a key is nearby. And if the key is nearby, it would receive that signal and send back an acknowledgement. After that, the car would send out a challenge associated with the car ID, which the key would answer if the car ID matches with the key. That's to guarantee that it's the same car that you're talking to. And then the response is sent back. If it's correct, the car door will open. So there are optimizations to the system where we don't require 2 round trips, but only 1. But this is the basic outline of how it works. Some key things to note here is that the car uses low frequencies to communicate with the key because it is how we bound the distance. So that ensures that the key is within the range of 1 to 2 meters. And this is also energy efficient. So you don't want the car battery to drain if it keeps communicating and not getting received. And then the key, on the other hand, uses ultra high frequency and can travel up to 50 to 100 meters. All right, so now we're moving on to how to attack this system. So because this challenge that I just mentioned is cryptographically secured, replay attacks are basically impossible. With the added nonce, every time the challenge will be different and the response will be different. Do you have a question? Oh, sorry. Okay. And another added layer of difficulty is that it requires physical proximity to the car in order to respond to the messages sent by the car. And the solution to that is relay attacks. So this is a quick graph to show how relay attacks work. It's very simple, and it's kind of a review from class at this point. So we need 2 attackers, one stationed near the car and the other stationed near the car owner who holds the key. So when the car probes the channel to see if the key is nearby, that signal will be picked up by attacker 1. It will be sent to attacker 2 through a private mean, and then attacker 2 would play out that signal to the car owner. So this way, the key would receive that signal and then start to message the car back. And that signal will be sent to attacker 2, and then to attacker 1, and then back to the car. So the effect of this is that the car thinks the key is nearby, thinks it's where attacker 1 is. And that would allow the car to be unlocked, and attacker 1 could get in the car and drive away. Some key insights here is that this attack is entirely within the analog realm, which means that all the cryptographic things are done in the digital realm does not matter to the attackers. They could easily propagate a signal without even knowing what the signal is. So there's no protocol, they don't have to identify the protocol and figure out how the protocol works. And this also has a very short delay in the matters of hundreds of nanoseconds. And the authors mentioned that other attacks at a time, so this is an older paper, this is from 2011. So the authors mentioned that the other papers that have done similar relay attacks usually translate a signal into the digital realm before propagating it over a certain distance and then translating it back to the analog realms. That would have a delay of microseconds, hundreds of microseconds. And this is done over tens of meters, so it's definitely far away enough for the car to be stolen without the owner knowing that. Here are two example attack scenarios. The first one is in a parking lot, very similar to what we just described. The key is that because in a parking lot, there's usually a common exit or an elevator, the car owner would probably wait at the elevator for a certain period of time. So one attacker could station there to have access to the key into which like a time window. And then the second example that we haven't mentioned is if you're a homeowner and you own a car, say if your car's parked outside of your house and you're traveling on vacation. So you probably would not bring your car key with you. And if you left it in the open and the attacker could see where your key is, they can probably very easily have access to the key through like a window and then relay that signal to the car parked outside and then steal your car. And then some additional implications of this specific attack is that once the car has been opened up and started, the car cannot stop anymore, basically, because your system would detect whether the key is actually within the car, but even if it detects that the key is not within the car, it cannot stop in the middle of driving because that's very unsafe. And some car models would sound an alarm, some would limit the top speed, but nothing is stopping the car thief from actually driving your car away. And then because of this, there's also no trace of physical entry. And if we're trying to claim insurance or trying to sue someone, there's no physical evidence left behind. So it makes this attack very strong in a sense.
Okay, so how we can defend how we can stop that stealing our cars? Any idea? No? I can steal your cars. You're not concerned? Really? How we can defend? No? Really? Okay. We have two variables that we can modify, signal and distance. Oh, sorry. That is, well, this should be distance. So, okay. And about the signal, the easiest way and the cheapest way is to buy something like that. You can buy it for $10 and you can stop stealing your cars just by blocking the signal. If the signal is blocked, so the attacker cannot use your key signal and open your car. That's the way. And also you can also, of course, remove the battery. And that's another way to stop the blocking the signal.
You need to always.
Yeah, of course it's not.
Take it out.
Yeah, it's not convenient to remove the battery from your switch, but
Even the shielding, you have to take out.
Yeah,
your
exactly.
each time and then.
exact. Yes, and also, of course, the manufacturer can change the software up there to press a button or switch to kill the battery, but they are not convenient. Okay, you should do the whole point of the case is like, okay, I want to start my car easily. I don't want to press my button. It's not luxury, so that's the point, no? But for these methods, actually, they are not working. The whole point is different. So yeah. So another thing about the distance, if there is a way that we can calculate the distance, okay, so maybe we can stop this, okay? If we can find that, okay, our key is not near our car, so we can stop that, stealing our car. And how we can do that? Okay, we can measure the time delay, and we can find out, okay, if the delay is a lot, so we can stop. You shouldn't open the car if the delay of the challenging and response is a lot. Okay, so that makes sense. Okay, if there is there's a distance between the signal, or also there's something like amplifier. They all have delay. So if you can find that, that's perfect. Okay, but the point is, first we should calculate distance very accurately. Okay. Otherwise, if we have a delay in calculation, if you don't have a stable time to calculate the whole point, it doesn't make sense because you don't want to. It's like you have a delay at 20, 15 nanoseconds, and you see the previous slides, the whole delay of the 30 meters is like 250 nanoseconds. So that's the point. So we should find, and also, but the good point is that people shows that, okay, we can calculate the whole distance needs. It's like the picoseconds. So that's perfect. So we can stop stay on card with calculating the distance. Related works.
Yeah, so the paper also talks about some related works they referenced. The main one is just cryptographic attacks. So basically, this is more research focused on these vulnerabilities in cryptographic algorithms for remote key entry systems. And basically, these vulnerabilities are mostly due to having short keys, which enable weak encryption and like side channel weaknesses, like we talked about. And manufacturers are also basically moving based on this research towards more secure ciphers. And basically, but the problem is relay attacks still remain a problem, as you can just bypass the encryption by directly relaying signals. And so that's just another issue. And a second one is just jamming and replay attacks. So basically, this uses radio jammers to prevent the cars from actually locking. So you can, similar to relay attacks, it's kind of you just eavesdropping and replaying these key signals to gain access without jamming. So basically, this just affects the car's start mechanism. And so basically, some countermeasures to this include cryptographic protocols with counters, or just like challenge response techniques, which basically just allow you to negate whatever jamming or replay attack is occurring. So just, yeah.
Okay, so we saw that, okay, we have a good attacks, and we can actually, they mentioned that they have a successful attack in 10 models car and so on, so on. So I want to discuss about do we have any ideas that don't look at it should be easy and secure, because the whole point of the definite method was, okay, like something like using your phone to unlock the car, okay, that makes more sense. It's much easier, it has a lot of sensors. So yeah, so maybe after like a 2011 we have like some ideas. So like your Tesla, you can open your Tesla with your phone, and it's much more convenient and more secure. That's it.
Can you do relay attacks on phones either?
We can, yeah, but we can use other sensors too. We can use a GPS. Okay, if your phone GPS and your car GPS is like near together, so we can open your car. Okay, so we have much freedom in the phone. Okay, but in the PKS, okay, so we don't have a lot of sensors, so we have a problem. So yeah, that's it. And other ideas, if you want to mention any question.
Is that it?
Yeah.
Okay. So yeah, one idea is using sensor fusion, but also the problem would be like, is your GPS, for example, accurate enough? Because like these things are like, these attacks should happen within like 1-2 meters, right? And then if it's like 5 meters away, it shouldn't work. But if your car is parked near your house and then you're inside, your GPS probably show you they're nearby. But I like the fact that user sensor fusion definitely is an idea. Questions? Yeah.
One idea would be to just constantly like switch what frequency you're operating on, and then that way the attackers don't know what signal they're replicating, maybe.
But they're looking for the signal that coming from the car, right? So, and then if you have a wideband enough antenna, because if your car key the car key also needs to understand that signal, right? So then you make the receiver on the key much more complicated, which is not an easy thing to do. But
I want to see
But yeah, definitely watch those videos on YouTube about how they can they actually like there's real videos that shows how one can do this. BMW specifically have very vulnerable to these attacks. Just FYI. Any other questions? All right, thank you so much. That was a great presentation. So whoever presenting first stays this side, and then you guys switch. Okay. All right, so last one is slightly different paper, and this is about kind of a defense and attack for detecting the presence of a device, right? So as I told you, fingerprinting is a big issue in wireless systems, and one can fingerprint devices in order to identify them. One can fingerprint devices in order to break their privacy. So both of them are important challenges, right? So this paper is particularly looking at BLE, Bluetooth Low Energy, as one particular modulation. or technology. It could be many other technologies as well, but BLEs, of course, is very common in low-end devices, so that's why it's very popular. Yeah, let's talk about this as well.
Hello, everyone. I'm Sammy. I'm here with Andrew, Cynthia, and Dom. We're going to be presenting on the paper Practical Obfuscation of BLE Physical Layer Fingerprints on Mobile Devices. Okay, so the basic problem is one of privacy in the realm of wireless security, specifically about BLE device tracking. So BLE, or Bluetooth Low Energy, is widely used in mobile devices like phones and smartwatches, etc. And they can be uniquely fingerprinted, as professors were saying, due to slight hardware imperfections that are introduced during manufacturing of these devices. And so these signal tracking, the tracking of these signals can be a privacy concern. And current countermeasures like MAC address randomization are not sufficient to deal with this because they operate at the link layer, and this is a physical layer problem. And so another problem is that countermeasures involving physical layer changes need to avoid making the device's transmissions harder to receive at the same time. Uh-oh. On a Mac user.
Where did you put it? There you go. So just press the next arrow.
There, thank you. Yeah, okay, so sorry about that. BLE beacons are transmitted by phones, smartwatches, and other smart devices hundreds of times per minute. They're used for many important applications like COVID-19 tracing, locating lost devices. They're used in like medical and retail applications, etc. And yeah, they make it possible to wirelessly track people's mobile devices. And so most devices also randomize their MAC addresses on a regular basis, like every 15 to 20 minutes. And so that avoids attackers searching for a device purely by MAC address, at least easily. And yeah, so like I said, fingerprinting can be done on consumer grade smart devices due to these hardware imperfections. And yeah, they can be used to uniquely identify these devices, which is a problem, as we will see.
Okay, so in order to solve this problem, we actually need a way to obfuscate the carrier frequency offset fingerprint by randomizing it. We can't just randomize it once, or else that sort of just becomes the new fingerprint. So we need to sort of do this periodically in a way that doesn't reveal the true carrier frequency offset. So within MAC address lifetimes, it doesn't make sense to randomize it then, because it still has the same MAC address, so you can still tell it's the same device. But then even across MAC address lifetimes, an attacker could identify that the two MAC addresses, when it changes, is still the same device. And so that's sort of shown here in the red. So when it's like, since it's the only one that changes, you can sort of still tell it's the same device. So so in order to do that, we need to randomize over time, but without revealing too much about the distribution, which would be able to show what the true carrier frequency offset is. So you could use a uniform or a Gaussian distribution, which provide different advantages. And so, or you can find a way to combine the two. So the proposed solution in the paper is to randomize the Gaussian random variable every time the MAC address changes, and then to randomize the uniform random variable every certain amount of times that MAC address changes. And so this provides kind of the good results of both the uniform and the Gaussian distribution, and minimizes the amount that the attacker learns every time the MAC address is changed. And so in order to actually implement this, that could be done through the tuning the frequency synthesizer, which can be done through like an API call, depending on the chipset, or by making baseband modifications to the signal.
As Dom mentioned, there's many different variables that come with the solution. You could either have the fingerprint duration be changing. You could use a Gaussian random variable and select your frequency offset by sampling your Gaussian, or you could use a uniform random variable where you could sample the uniform random variable. Each of these have their pros and cons, in addition to different sorts of implementation tactics. The key objective for the research team for this project was to delay an attacker for more than 24 hours. Because the idea of this attack was that the attacker would have to be standing within the same room, within Bluetooth distance from you. So you'd have a tough time being an attacker and following someone throughout their day for 24 hours. So as Dom mentioned, you can use a API call and set the frequency offset for the specific device. And by choosing very specifically when to make those API calls, you can then randomize in such a way that the attacker has a hard chance of guessing your device. During the evaluation, they actually collected data in public areas, and so they collected public BLE beacons. Then they introduce up to 20% of the devices in the area with the obfuscation, so they bring their own devices in. They had an example attacker that is both practical and optimal. The practical one was more of like a normal attacker that would just be like a guy with a laptop and has like normal understanding of what's going on. Versus the optimal attacker has predetermined the fingerprint of the device already and already knows the device and only just has to find it within that sample of the ones that are in the room. You can see that there's a couple of really interesting results that Cynthia will get off to. And I think the most important thing about the evaluation methodology was that they were focusing particularly on accuracy versus time. So if you have a very accurate device or very accurate attack, but after 25 hours, it's not very applicable to this case because again, the attacker won't be able to follow you for 25 hours.
Yeah, so now that these guys have already set up kind of the implementation, all the evaluation, we can look at some of the key results, right? Dom mentioned two different distributions that can be used to obfuscate the signal. Well, using the uniform distribution is actually better in a shorter period of time as compared to the Gaussian, just because of how averaging the distributions will give you kind of like the center, which as Dom said, you kind of know that the obfuscation is just like one more layer added onto your signal. So you can kind of just subtract that and get your signal back. So using different distributions, better in different timeframes. But when you combine both of them and use them hierarchically, which is the whole thing Dom was talking about with sampling, combining them actually performs close to a random coin flip, which means the optimal performance, the green line you see in these graphs is the attacker success rate of 0.5, which is basically saying the attacker's basically just guessing randomly, flipping a coin saying either this is the device that we want to identify or it is not. So you can see that in the bottom graph, which is actually checking between the hierarchical usage of the two distributions, that they stay close to 0.6 as the probability, even after a whole day of this attacker being nearby checking these Bluetooth signals, because due to the randomization every few Mach lifetimes and the resampling from the two distributions in a hierarchical format, the attacker doesn't actually gain that much information to be able to figure out the device ID. So those are the two main key points. Andrew mentioned some other ones on his slides, which are that if you have more devices around in a certain area, obviously it's harder for the attacker to figure out which device is which because you just have to filter out more signals. Whereas if you just have one signal sitting there, you can probably check it with an ID you have a little easier. But the key takeaway, the insight from this paper is that, as Andrew said, it's not obfuscating the signal is not a cure. Like you're not just immediately saying this device cannot be ID. You're just kind of preventing and increasing the amount of time that this attack has to happen before they can figure it out. So if you keep making it hard for the attacker, they're kind of going to give up, or like, they literally physically can't be close to you as in the same room as Andrew said. And that's kind of the main goal, which is just to make it harder for them. Some future work that the researchers actually mentioned is that right now this is done with Bluetooth Low Energy, whereas there's a lot of other wireless communication protocols we've talked about in this class. So like Wi-Fi, Zigbee, like the other groups actually presented earlier, if we could extend this research to those communication protocols, then obviously those will be secure too. And also
Sammy mentioned that the main hardware imperfection that's being obfuscated here is the carrier frequency offset, but there are other offsets like the in-phase and quadrature RF offsets and the nonlinearities introduced by the actual power systems and the devices that can also be obfuscated. So just expanding the range at which this obfuscation is used would help cover up a lot more of the device fingerprinting data that's available. And then we've got some discussion questions up for you guys to think about but we can read them yourself. Thank you. Any
Questions? What is the reasonable time what's the reasonable time for not being trapped? You think
A reasonable time.
that's your number 3 question, right?
That was mine, yeah.
Oh,
I don't know. I feel like you could set your reasonable time as like 24 hours, right? But then the attacker in 2 years is gonna have better capabilities or some sort of attack around you.
mhm.
And suddenly it's at 6 hours. And it's like, okay, well, you just said your valid case is 24 hours.
Mhm.
So it's really like a tough question to ask where the balance is between like verifiability and like, future proofs.
Yeah, that's a tough question. And then even if the attacker stays the same, there are some type of information that might be leaked in 24 hours, some of it that may not. So you never know. So it's hard. But also, I mean, work like this is valid because it's at least make things harder for an adversary, right? So
They were even saying there's more improvements that they have that they didn't try. Because like the number of max lifetimes over which they randomize is fixed right now,
Mhm.
but that could be randomized too.
Mhm.
They had to figure out like a seed for that, I think.
Yeah.
Okay.
All right.
Next
Any
slide.
There's more.
One more slide.
one more?
Yo.
Nice. Thank you guys. Appreciate it. Okay. So let's continue. So we are going to start a new topic called memory safety. Last week I talked a little bit about malware and say what happens when you're attacking a system. So this week we're going to actually go through the details of that and then talking a little bit about some solutions. And then the next few weeks, then we're going to talk more about solutions. And then your next projects will be also about one of these solutions. So just quick notes about the computer assignments. I think the second one is done. Of course, we will do some partial gradings in case you didn't fully submit everything and your code doesn't pass. For the next one, I already put it on the website. Feel free to kind of start it whenever you want. I think the deadline is March 10 or something. No, sorry, March 1st. So you have some time. And then I also put the fourth one in case that you have free time, because I noticed most people are kind of like busy at the last few weeks, so you can actually manage your times whenever you want to submit them or work on them. And there will be a fifth one which we're going to release on the finals week. So that's the time we're going to work on it. Like week 10 and finals week. Questions about the computer assignments? Yeah.
Just curious, I noticed all of them are released right now.
The up to 4. So there is a fifth one as well that's going to be released. Yeah. So what was your question?
I was wondering if there was a motivation for releasing all of them. Because like a lot of people are busy towards the end.
What do you mean? Like, why did I release it? Or I mean, it's going to be released anyway. So you're asking why it's released now, or what was your question? You can work on it now, right? Or you can consider it's not there and then just do it whatever you want. Yeah.
I can't get the PDF
What's that?
slides. I can't get the PDF of the slides.
Of this slides?
Yeah.
Say it louder, say it again.
The files in your trash file,
Yeah.
your trash folder.
Oh. Oh, you mean like my, interesting.
Yeah.
Oh, okay, let me see if I can do it now. Just a sec. Okay. So. Let me know if, like, give it a 1 or 2 minutes, usually takes some time to update. All right. Any other questions? Yeah. Yeah. Yeah, I'll update you about that. India, yeah. Actually, next, in the next, on Wednesday, I'll talk about. All right. Any other questions? Did you figure out if you want to ask your question again, or you're good? Okay. All right. So, as I said, we are kind of like, so far we talked about kind of like manipulating physical world, working with the physical world and those kind of things. But what we want to do now is kind of corrupting the memory itself. So kind of corrupting the system from within, such that then we can do multiple different things. What can we do with it? Then we can obviously do things such as what we call data-only attacks, which we either gain some knowledge from the system or corrupt the information in order to achieve another leverage or advantage. Or we can do what we call a hijacking the control flow, essentially allowing us to run any arbitrary code that we want to have. We're going to discuss this extensively. So the major problem with when we are talking about memory corruption, usually is because of these unsafe languages. C++ is a great example of those. And these programming languages allows you to do things that are not necessarily safe. Okay, I'm showing you a common example, and that is kind of invalid dereferencing. And you can think about invalid dereferencing as kind of two different types of invalid dereferencing. You can either have like a temporal dereferencing, which we usually call it dangling pointers. A popular example, a common example, is what's called use after free. For example, you have a pointer called foo, and you free this foo, but then later on, you're going to use this foo after it's been freed. And in many cases, this is allowed in C++. And if one can do that, then they can actually kind of write things to foo, which used to be this, but now it's something else, because now I freed this, so the compiler or the system can assign some other secret information or some other memory to this location. And now by changing that location, I'm basically corrupting that specific line of the memory. Also, what we can do is what we call out of bounds pointers or spatial kind of dereferencing, which, for example, if your foo is supposed to be only 40 characters, if you somehow can do like foo 42 and then don't really check the bounds, then you're essentially writing things in other areas of memory that you're not supposed to, right? So you were supposed to only write things into that 40 character or 40 array. Generally, the kind of like the violation that we are talking about is you're not supposed to read or write or free a memory that you normally would use, right? And there are many examples of this. We're not going to go extensively talking about these various different types of unsafe languages, but if you're interested, definitely go and read this paper, which is kind of like systemize this types of memory dereferencing problems. But these are just examples of this. The reason that we cannot fix these is because of the complexity of the programming language. Many programs have been written, for example, in unsafe languages such as C and C++. The assumption was that the programmer would have been able to catch this and fix these issues. But once these programs get more and more complicated, then this becomes a very manual process, very error-prone process. That's why we have these problems. You had a question?
Oh, no.
All right. And then you had a question? Yeah.
How did the attacker have access to this thing?
How did the attacker? So for example, let's say you have a piece of program that's receive inputs, right? So if the attacker can kind of like, write a program this way, right? That is, it's freeing the foo, but intentionally trying to access it after being used. Then that's going to be the problem. Another thing is, if this is a bug in your program, right? So the attacker can observe this bug and then use it for their own intentions. So we're going to actually talk about like real examples of how this attacks can work. To kind of like give you a more high-level picture, generally memory corruption one way or another could result in various different problems. It could result in integrity, and then C and D here means more of code and data. So it could corrupt it could affect the integrity of your code, or it could affect the integrity of your data. It could affect the integrity of the pointer or the value that the pointer is pointing to, like the memory content. And then, as I said, it could be either the code or data. Additionally, it can use the location, the data that's been actually stored there, and corrupt that using this kind of like integrity approach. And if we do that, then we have things such as code corruption, that we essentially change the code into something arbitrary, something that we want to do. And then there are attacks that this could be useful. With the same thing we can do with data, and this is what we call a data-only attack. So, for example, consider that this data that's stored in this memory is a particular, like, number, I don't know, like a specific password. By corrupting this, you're essentially corrupting the password. Or let's say this is a privilege bit. By corrupting this, you're changing your privilege levels in the system. And then lastly, you can even use this in order to launch another more sophisticated attack. And this is what we're going to talk about in this lecture. And that is the main one, is what we call the control flow integrity attack, which essentially by corrupting and then using that data that we have corrupted, then we can actually launch something that's very, very powerful. You can also corrupt and then use that data for doing, again, something more powerful. For example, if I change the privilege and then use that privilege, that data, in order to then, for example, call another function and then use that function as like a root level access and so on. So there are kind of like layers of attacks that can start by just corrupting the memory. But if you corrupt the right thing and then kind of chain it together with some other techniques that we're going to describe, then that will lead into very, very important and very interesting attacks. And examples that I'm going to talk about particularly is buffer overflow. This is the example of kind of this route here that starts from the memory corruption, goes to the code, and then use the code in order to do what we call the control flow hijacking attack. Okay, so we overflow the buffer. I'm going to describe what is a buffer and how do we overflow it. And eventually, we want to be able to run arbitrary code in the system. Okay, the reason that we are interested in that remember that last time we talked about all these different malware and say that, oh, the malware needs to kind of inject it and then needs to be executed. So this is how we're going to kind of connect the dots here, that we corrupt the memory, we run the arbitrary code. That arbitrary code could be the malware that we have somehow installed in the system. Okay, so let's see how. Probably some of you are already familiar with buffer overflow. Show of hands, how many of you have heard and used buffer overflow before? Okay, so everybody knows. So let me quickly go over it. Feel free to ask questions. So this is generally how we lay out the memory, right? So for every single process, we have a format like this. This is extended x86. The important part in the middle is the heap and stack, which kind of grows, right? In opposite direction. Most systems, the stacks goes downward. In other systems, it could go upward. Doesn't matter. It's just one direction that goes up and down. The important things that cause buffer overflow to work is this thing called calling convention. So generally, when we have a function, usually wants to write, code in a modular fashion. That's why we use different modules, different functions, and we kind of like use them, call from one to another, and so on and so forth. It's just for making the code more manageable. And in order to kind of make sure that your code functionally is correct, you follow this calling convention, which essentially kind of like you say that, oh, okay, if I want to call a function, here are the things that I need to do. Once I want to return from that function, here's some other things that I need to do that I'm going to describe in the next slide. And then in order for that to work very quickly, for those of you who are not that much familiar with computer architecture, how the system works, you usually have your CPU here and you have your memory here. Most of these systems that we are dealing with is this store program order system, which means that your code stores in the memory. And in the CPU, you have usually this register called program counter or PC that kind of points to the instruction that needs to be read from the memory. So your program, essentially think about it as kind of like a line by line instruction. The PC kind of starts from the top, read this instruction, execute it, and then go to the next instruction and execute it, and so on and so forth. Okay. So in order to actually execute a call or execute a return, what needs to be done is that we need to change this PC to another address that kind of so let's say this is your main function, this is your foo function. So in order to call a function, all I need to do is basically changing where this PC is pointing to from the beginning of the main to beginning of this foo. And in order to return back to the main function, all I need to do is that once I reach to the end of this, let's say that, for example, the call function happens over here, I need to return back to I was before, right? So I need to kind of remember what was the address I was in main when I called this function. When I'm done, I need to change the PC back to that address, and then from there I can basically resume, right? So think about basically the lifetime of the PC is what decides what function is executed, right? So you execute some instructions, then you have a call function. So say that, okay, I remember where I was. I'm going to jump into that function by changing the PC. I'm going to start executing this. I'm going to reach to the end. I'm going to see this return instruction. The return means that go back to where you were, which means that I was here. So I remember this number somewhere. I go back to there, and then I change the PC to that. And then from that, business as usual. I just continue executing, right? This is like basics of any sort of computer system. So for this to work, we usually use the stack, this part of the memory that dynamically kind of like store things. And as I said, we follow this calling convention, this set of protocols. The protocols kind of looks like this. As I said, your kind of like your memory looks something like this. You have your stack that kind of goes downward. And then the way it works is that when we have a function, let's say this is main function, and the main function is what we call a caller. It's the one that calls the other function. So the main function has its own stack frame. It has its own thing to work on. And usually that's kind of like this part of the memory, like the higher part of the memory, because the stack grows downward. Then we reach to this call function. So in order to call the function, it's not just changing the PC. We need to do some other things as well. The main two things that we need to do is we need to push the function parameters into the stack, because when you're calling the function, very likely you're going to, read some inputs, right? You're going to pass some values to that function and say, okay, these are the inputs to you, go and do things with it, right? And this inputs could be a very large input, so you cannot just use the register. So that's why you usually pass in the function parameters, push them into the stack, and then call that function. The second important thing that you need to do is that before jumping into that function, you need to save the return address. And as I said, if I have like a main function like this and my foo function is this, and I'm kind of executing here, 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 and then at this point, for example, I reach to the call function that goes here, I need to remember this next address, and this is my return address, because once the foo is finished, I need to go back and continue my main, right? So I need to save this address into this stack as well. So I push that into the stack as well. Then, of course, I need to kind of say that, okay, where I was before all of these things, and this is what we usually call a frame pointer that kind of points here. This is before all of these madness starts to happen. This was the last point from the previous function, right? So I also stores that, and we usually call that, the frame pointer EBP if you're using x86, and so on and so forth. And then finally, we have the local variables for the new function. So because the new function also has lots of local variables, right? Those local variables are going to be stored here. And then how many we have, like it's just going to just grows the stack, right? And that's where this would be basically the new frame for this new function. If I have another function, then the same story goes over and over. So like, you just continue growing. And then when you're done, you kind of like go back up. Your stack pointer going to point back to this point. And then you can basically overwrite these parts as you wish, right? So this is the story of how a calling works. Any questions here? Cool. And then, of course, there is same things you need to do when you're returning. So this parts I already talked about. And then, so when we are returning, we kind of need to do this in the opposite direction, right? So of course, the first thing we need to do is that we need to return the value if your function is returning something. That's usually, you don't put it into the stack, you usually put it into a particular register. For x86, this is EAX. Then you need to kind of restore the stack frame. So basically this base pointer needs to be updated to say that two points to here, to where it was before. So you're trying to kind of backtrack what you did. And then the most important thing is that you need to go to this return address. You need to read this value, whatever this value is, and you need to put that into your PC, right? So you need to update your PC based on this value. And this is a very, very important part of this calling convention, and that's the part that's going to be actually misused by an attacker, that whatever value is stored here, I'm not going to care what value this is. Whatever this is, I'm going to put that into my PC, right? So that's really how a calling convention works, okay? So the idea of the buffer overflow is this very simple question. So can I overwrite the stack, right? And the answer to this is yes, I can. And if you go back to this kind of like picture that I showed you, I told you that there are ways to corrupt the memory, use after free, out of bound, other temporal attacks. So for example, let's say this buffer, whatever this local variable is, this is the one that actually has this vulnerability. So what I can do is that not only I can kind of overwrite this value, I can overwrite everything upwards, right? So I can basically go all the way up as much as I want. And that means that I can overwrite this return address, I can overwrite this base pointer, I can overwrite this function parameters, I can even go back up and overwrite previous functions values as well. I can do as much as I want, depending on what type of memory corruptions that I have. But as I said, since these unsafe languages has lots of these problems, then it's not that hard to kind of override this. So probably most of you have seen and heard about SDR copy. This is kind of like the most famous types of overwriting these things. Essentially, you copy one string to another string. If you don't check the bounds, you can basically copy as much as you want on the system. Okay, so what we can do is that I can overflow this buffer, this local variables as much as I want. Okay, and that's an important thing that you can do. Another important thing is this can even be more significant. So first of all, by writing into a local variable, what I cause is I'm changing the stack. Okay. And this should not be happening, right? So this is a bug. It should have been caught by the programmer, but as I said, the problem is these codes are getting very, very complex that the programmer forgets to do these checks. That's really what's happening here. But I mean, I can write these things and I can have like integrity and so on. But the question is, can I do even more sophisticated things, right? So the idea here is, if I can overwrite this, and based on what I just said, that the way that the return function works, what I can do is that I can overwrite these things, but I can be very careful about what is being overwritten at this point here, right? At this point in the middle here. If I can write some specific thing here, if I can control what I'm overwriting and then put something specific at that point, is then what will happen is that when the return function, when return instruction is going to be executed, as I said, the only thing that we care about is whatever value is stored here is going to be the value of the PC, right? So as a result, if I can I overwrite arbitrary values here, I essentially can force the system to jump to wherever I want in the entire program memory, right? So I have this unlimited capability, this very, very powerful capability that by just overwriting my local variables and then kind of engineering this such that the value that's been written here is the value that I want, then I can force this system to jump to wherever arbitrary location that I want in the memory, okay? And this is what we call a control flow hijacking, because essentially we are hijacking the control flow. The control flow means this, right? This was the main function. We kind of like running it like this. We reach to the call function. We run executing this foo function. And the plan was once we get to the return, we should have come back to this point and continue running this, right? The plan was we need to finish the main function, the parent function. But now by executing this return this way, instead of going there, I'm hijacking this and saying that, oh, no, you actually have to now execute the function that I want, right? And then that function could be anything inside the memory, could be the function that the attacker kind of injected prior to this attack, could be any of those malwares like ransomware or anything like that, right? As far as I can somehow put this into my memory, and I'm going to describe how we're going to do that, then we have this powerful capability of running that code inside my memory, inside my system, okay? And this is what we call a control flow hijacking attack, okay? So what should we put there, and what's usually jumping where, and what should that be? So generally any malicious code will do. Like this depends on what the attacker wants to do, and usually this part is what we call payload. Okay, so the attack has this kind of attack section that you kind of overwrite and overwrite the return address. Then there's the second part that this return address actually gets executed and kind of start executing the code that you wanted to. We call that code payload, and this payload could be anything, okay? A very common payload that many systems use is what we call a shell code, okay? A shell code is essentially this piece of code that invokes a shell, okay? A shell that you use if you're using like a Linux systems, you've probably seen like a terminal. It opens a new shell for you, and essentially once you have a shell, then you can execute any arbitrary program you want on that shell. You can send and receive data. You can create and modify files and programs and so on and so forth, right? So one of the main things that the attackers wants to do is creating some form of invoking some form of a shell. And in fact, invoking a shell is very simple, because in most of these operating system, including Ubuntu, invoking a shell is essentially just making a system call. Okay, and what very particular system call will invoke a shell. So all you need to do is a few lines of code in this payload in order to invoke a shell. Then now you have a shell, and now you can do whatever you want with that shell. You can run any arbitrary programs from there. Okay, so what doesn't need to be a shell code. It could be a particular payload that you want to run. For example, all those things that I described last time, different types of malwares, they could go here. Okay. So this is kind of like, the algorithm, the step-by-step algorithm for doing this attack. You find a memory safety vulnerability, something like, use after free or out of bound access and so on. Then you kind of like write your malicious shell code, or generally any sort of payload that you want, in a particular known memory address. You somehow inject it, I'm just going to talk about. Then you're going to actually execute your attack. You're going to actually overwrite the memory and put the return address to the beginning of this shell code. Then you let the code to execute and return, and then boom, you will have your shell code or payload being executed. Then you can do whatever you want with it. So from this point, is basically the attack is successful. The attacker takes control. They can do whatever they want. Okay. So the question becomes that, okay, how do I even, inject this shell code? Because now I talked about I can just crop the memory and force it to jump somewhere. But what if I cannot really inject my code there? Okay, so there are two solutions for this. The first one is I can also inject my code as I'm overwriting. So when I'm overwriting this buffer, and instead of overwriting it with junk, I can actually overwriting with the code that I want to execute, and then execute my buffer from there. So for example, let's say if you remember, I said that like you have your buffer here, and you have your base pointer, and you have your return address, right? And then I basically say that I can just kind of like overwrite this until I kind of like overwrite the code here. Then what I can do is that I can put the address here to beginning of this thing that I injected myself, right? So I basically say that this is not an arbitrary location. This is actually the beginning of this shell code that I have here, right? So I not only I overwrite, but I also inject the code that I want to execute with this, right? So that's very powerful again. The problem though is that I need to know exactly where this code begins, right? So it will require an additional amount of engineering to know where exactly is this, because if I'm wrong by even 1 byte, then the instruction is completely kind of messed up, right? In order to fix this, there's this kind of landing area that we usually add. So we're not really adding the shellcode at the beginning. We add our shellcode in the middle, and then we have this landing area, which is just no operation instructions. If you're not familiar with no operations, think about an instruction that doesn't do anything, okay? So we're gonna basically first pad the buffer with this no operation sled or landing area. Then I'm gonna start executing this shellcode. The benefit of this is that now this beginning address could be anywhere in this landing area. So if I'm mistaken by a few bytes, nothing bad will happen in terms of the attack, because I'm gonna execute some no-ops, either like 5 no-ops or 2 no-ops or 10 no-ops, doesn't matter. But eventually I'm gonna run my shellcode, and that's what matters, right? So this is kind of like buffer overflow plus code injection attacks together. The problem with this, in terms of the problem, or actually the defense for this, is that what you can do is that you can make the stack non-executable, okay? Which means that people have learned that this is a big problem. So what they do is that they don't let code to be executed from the stack itself. So make the stack, or make some pages within the stack non-executable, makes this attack go away. So you can still overflow the buffer, you can still kind of overwrite the return, but you cannot write arbitrary code and execute that arbitrary code from the stack itself. Okay, so you are back to square one, which I need to find another way to inject the code. There are two interesting solutions for this in the attack community. One is what we call a code reuse, which the idea is that I don't need to really inject code. Maybe I can reuse the code that exists in the memory and use it for malicious purposes. And a big example of this is what we call return to libc attack, which means that there are lots of these kind of standard libraries like libc, like printf, scanf. These are all part of libc. These ellipses actually have sections of code that are indeed actually useful. For example, I told you that in order to kind of like invoke a shellcode, all I need to do is calling a system call with a specific identifier, okay? And this libc actually is full of those system calls, okay? So what researchers found is I can essentially jump into part of this libc and then force it to kind of call, create this system call with this particular input. And that's all I need to have in order to invoke a shell. So I really don't need to inject anything. All I need to do is finding where those libraries are stored in the program memory. I just jump there and force it to create a system call. Okay, so that's what one thing that people have done, return to libc. Another thing is what we call return-oriented programming, or ROP. The idea of ROP is that a piece of code might not be useful for doing something malicious. But if I run smaller piece, like run gadgets of this, then I can do something meaningful. How? This is, I think, one of the papers that's going to be described next week in the paper reading, in the paper presentations. But the idea is that I can basically do this, that I have the control to jump to arbitrary locations, right? So instead of jumping only once, I can keep jumping back and forth. So I can basically jump somewhere, run one instruction, jump back, kind of return, and then again jumps again and again and again. So I basically, instead of like storing one address, I store a chain of addresses. These are the places that I want to jump into. So the first one I jump, I do some, so I point to that instruction. I do one instruction. And then if the next one is a return, I'm essentially just jumping to the next instruction and then the next instruction. So if I have these things called gadgets, and the gadgets are sequence of instruction that ends with a return, essentially all I need to do is that if I jump to the beginning of this, when I reach to the return, I'm essentially going to jump to the next one, to the next gadget, and so on and so forth, right? Because each return is essentially looking at the address in the stack, and I already planted my stack with this kind of malicious addresses. So each return will result in invoking a new gadget and a new gadget and a new gadget. And if I basically, in terms of the attacker, what's really being implemented here is this, right? So this one, this one, this one. I don't care really about this one, this one, this one, this one. So it's really, I'm kind of stitching these gadgets in order to create a full program. And the interesting thing is that people have found that this is actually a Turing complete model, which means that essentially you can do any arbitrary software by creating these gadgets. And there are many, many, many of these gadgets in your program memory because x86 is designed such that it's a CISC. It means that, you know, the size of instruction is variable. So creating this kind of instructions ends with the return is not that difficult. It's actually very easy. So in other words, the attacker can kind of scan through the program memory to first find these gadgets, find their addresses, and then basically what it does is chaining these addresses in the stack by overwriting and doing the buffer overflow. And what will happen is that the attacker basically essentially execute these red instructions one after another in order to create the sequence of instructions that they want. Right? And this is a very powerful attack because it doesn't need to inject anything. It doesn't even need to kind of assume anything about your system. And as I said, it's Turing complete, which means that it can basically do any arbitrary program as your normal programming would do. Okay? And then more details of this we're gonna be discussed next week when people are gonna present this. Any questions so far? Yeah.
How is it Turing complete if you can only use like libc consistently?
No, it's not just libc, right? So that is just the return to libc, but this ROP could be any part of the memory.
Right, then how is it Turing complete? Because aren't you limited by what's already in memory?
It is already in memory, but what they found is that essentially you can have any arbitrary instruction in that. So the probability of finding any arbitrary instruction in a large memory is like 99.99%, which means that I essentially have all the instructions at my disposal, so I can do whatever I want. Yeah.
So, I mean, is it just also relying on the statistics to like find the operand that the attacker wants? For example, in those, x86 commands.
You mean the operands?
Yeah,
So
changing the operand.
Yeah, the operand. So that's a good question. Your operands you can also you can also manipulate with this. So again, finding operands is also not that difficult. You need to find these move instructions essentially with some values, and then again, those are lots of them that you can find. But again, usually when you want to do RUB, you don't need to do very sophisticated code. All you need to do is usually just creating invoking another shell, because once you invoke the shell, then you can run your arbitrary code there. So there is no point of run your arbitrary code using RUB, but the point is you can technically if you want to. All right, so how common is this in just in general? This actually, all of these attacks are very, very common. This is like one of the most important kind of part of the security systems. And almost all of these common, software attacks. This is a 2020 table. And as you can see, all these CWEs are all, various different form of these memory corruptions, like out-of-band writes, out-of-band reads, I mean, cross-site scripting is a different thing, but all of these like memory buffers, so all like top 10 SWEs, CWEs, sorry, are all usually this some form of memory corruption. Okay. So now the question is, how do we defend? And that's the part we're going to focus a little bit more in this lecture. But as I said, if you're more interested in learning about these different types of attacks, definitely go and read that SOK paper I showed you. Next week, I think there will be 2 attacks that your classmates going to also talk about. There's one data-only attacks, and the other one is return-oriented programming attacks. All right, so let's also talk about defenses. And there are various different types of defenses that one can do. First of all, the easiest thing to do is getting rid of these unsafe behaviors. Like getting rid of memory corruption altogether will fix many of these problems, right? So using type-safe languages, like things like Rust that people are using these days, instead of using something like C, C++, could fix lots of these problems. Unfortunately, the main issue with this is that there are lots of systems that are already deployed systems. So in other words, we have lots of legacy systems that you cannot just say that, oh, let's change this into let's change this from C to Rust, because that requires, millions and millions of dollars of investment and development and so on and so forth. So it's not like an easy task to do. Like, your Linux kernel, for example, has been written in that. And not only that, is you also will use some, you will also lose some efficiency, because like program language such as C's are very, very fast. So it's just also important to know that. Then we have a bunch of different other solutions, such as you can have like checks at the compiler level in order to fix these issues, right? Removing this potential vulnerabilities. Then we have also all these like the different other methods, including stack protection, CFIs, pointer authentication, data execution protection, ASLR that I'm going to briefly talk about. So the first thing that we are talking about is the stack protection. Okay, one of the key things that people have used in order to protect our system is what the idea of what we call stack canaries. Okay, so if you remember, if you remember the way that stack was kind of like showed was you had your return address here, and then you had usually your base pointer here, and then you had your local variables here, right? And then the problem was that if I want to kind of like overwrite, I overwrite this direction, I overwrite this, and then I eventually overwrite the return. Okay. So the stack canary basically has this very simple idea that between the return address and the local variables, let's actually put some random number here, which we call a canary, as in the bird. And the idea is that if this return address is modified, it is guaranteed that this value has been modified as well, right? So if the return address has been overwritten, prior to return address, the canary should have been overwritten already, because it's kind of like it's a lower location. So it has to be first canary that has been overwritten, then the return address has been overwritten, okay? So based on this simple assumption, the idea is that whenever I want to return, okay, in order to see whether that value has been overwritten or not, I'm going to first check whether the canary is the same canary that I expected or not. So in other words, whether my canary is still alive or not. If the canary is not been modified, then it is guaranteed that the return address is also not modified. So it's safe to do the return. If the canary is indeed modified, then there's a high chance that the return address has also been modified. So I'm not going to execute this return address. Okay. So that's kind of like the basic idea of the canary. Of course, it has to be between the two. Otherwise, if it's like upper side of this, then it wouldn't be helpful because the attacker can stop overwriting things up until return address and nothing after. And then question.
Would this be a denial of service vulnerability? Because then the hacker could keep writing to it and then know that they can be executed?
Yes, but usually so the question is whether this could be a denial of service. Yes, if you override the canary, then you kind of like eliminating the chance that this function operates normally and returns normally. But usually when you kind of do it once, you're probably not going to run that function again. So it's not like, you constantly kind of like calling that function, the attacker kind of override the canary. So one time, yes, multiple times, probably not, because you probably don't do it anymore. Oh, yeah.
Like, can the attacker overwrite the return address without overwriting the canary? Like, say if you were accessing like something out of bounds in an array, but not everything in between.
So the idea is that your stack is like this, right? So your local variables, the things that the attacker can access to are here, okay? Your stack, your canary is here, and your return address is here, okay? So the attacker can essentially access virtually any points in this buffer, right? But in order to overwrite, they have to kind of engineer such that somehow it skips this and overwrite this, right? And people initially, when people actually start talking about stack canaries, they show that this is very hard to do. Although there are attacks that actually indeed shows that this is manageable in under very specific circumstances. So if you're doing out of band, for example, let's say it's your 40, this one, let's say, I'm just simplifying it. This is 41. Maybe I overwrite up to 40, skip 41, and then overwrite 42, which is the return address. It's doable. It's much harder for the adversary to do that. Yeah, you had a question.
I was gonna ask the same thing because presumably the attacker knows where the return is located, right?
Yeah, so the idea is that, I mean, the reason that stack canary works most of the time is that you cannot have like selectable write. If you're overwriting everything because you're overwriting a buffer. You're not saying that, oh, I'm overwriting this and this, right? But yes, technically under some special circumstances, one can do that. Yes.
Isn't this a non-issue in systems that are like not embedded system? Because I imagine an embedded system doesn't have like a page table, but in most computers you have a page table where you can just mark that only instruction memory should be executable, and then all other obviously should not be executable. So is this a non-issue?
So no, so this is not about, so I'm just overwriting the returns. I'm not executing things. So what you're saying is making the stack non-executable, which both embedded systems and non-embedded systems have that, okay? Here, what we're trying to do is I'm just trying to overwrite the returns. I'm just trying to corrupt data. I'm not changing any code, right? If that one was when you're injecting some code into your stack and say that, oh, my stack cannot be executable, so then I'm kind of eliminating that. But here is, again, you overwriting the return address, which is the number. It's not code. All right, so this is one, but as you guys pointed out, there are attacks for stack canaries that actually indeed can be overcome and can be attacked as well, unfortunately. If you're interested in the stack canaries, I'll definitely recommend you to go and read a little bit more. The second is that exactly what you said. This is what we call data execution prevention, or DEP. So essentially what we're trying to do is that saying that part of the memory should be non-executable, which means that this limits the capability of an attacker to injecting things and execute those things. If I make the part of the memory non-executable, which means that even if the attacker injects things here, they cannot execute it because this is non-executable, right? So usually what we do is that in order to make things secure, data part of the memory, the parts that's kind of interacting with the physical, with the outside world, if we make them DEP, then we are secure against code injection attacks. The problem though is that it's not easy to make everything depth, because you have these things called self-modifying codes that it wants to kind of like read some data, and based on that data wants to make dynamic decisions, doing this and doing that based on the input value. As a result, you cannot just say that, oh, entire part of my memory is non-modifiable, non-executable. There are part of the memory can be modifiable and executable at the same time, which again creates this problem. So it's kind of like the convenience versus security issues. So you want to have both at the same time, and that will cause some problems. Lastly, there is this thing called address space layout randomization, or ASLR. This is also a common practice and standard in almost all the systems. The idea here is that make it harder for the adversary to predict things, okay? So the idea of ASLR is that if I know, for example, this block is here at this address, then the other block is here at this address, then it's much easier for the attacker to predict what is the return address, what is the address that for example, the malicious code is also stored somewhere into the memory. But if I kind of randomize these positions, every time that I reboot my system, if I kind of move things around, okay, then it would be very hard for the adversary to kind of know where the beginning of this function is, what is the return address, where is it stored, where is the malicious code is stored, and all those things. So even though the attacker can corrupt things, still can corrupt things, successfully, but this corruption will not lead to anything meaningful, because essentially everything's kind of shuffled. You shuffle everything all the time, and this will result in much harder attack scenario for the adversary. Of course, there are also attacks that shows that one can circumvent ASLR using other techniques, but this is also very common in many systems in order to detect that. Okay. All right, so the another thing is what we call control flow integrity. That's actually what the thing that we're going to focus a lot in the next lecture, and this would be part of the projects as well that you're going to do next, your CA3 basically. All right, so I'm going to pause here, and then once we come back on Wednesday, I'm going to start talking about this and how we can use this in our systems.